All right, so we are going to start with the first video of Cal 2. So we're going to actually jump back into Chapter 3 because there is a section that the Cal 1 classes here at Mississippi State don't cover that we're going to need throughout this Calculus 2 class. So we're going to jump back to section 3.11, which is actually hyperbolic functions. And we're going to talk a little bit about what hyperbolic functions are, and then maybe a couple of derivative rules that you haven't seen before. So first thing I want to do is define what these are. So there are actually certain combinations of the exponential functions, e to the x and e to the negative x, that you saw in Cal 1. They arise so frequently in certain math classes that it actually deserves getting a special name here. These are called the hyperbolic trig functions. So there are actually 6 of them, but really there's only 2 that I'm going to need you to learn explicitly, and that's these first 2 right here. So that is hyperbolic sine and hyperbolic cosine. As you can tell, they look very similar to how you wrote trig functions, except you add an h after your sine and your cosine and all the rest of these. That just represents hyperbolic. So a hyperbolic sine function is defined as e to the x minus e to the negative x, all divided by 2. And hyperbolic cosine is defined as e to the x plus e to the negative x, all divided by 2. So they're very, very similar to each other. Hyperbolic sine has subtraction. Hyperbolic cosine has addition. The other 4 hyperbolic trig functions, actually, you can just use a very similar identities that you've seen before in trig. Because in trig, we remember that tangent is actually sine over cosine. Well, in the hyperbolic world, it's actually no different. Hyperbolic tangent can be defined as hyperbolic sine divided by hyperbolic cosine. And then all of your reciprocal identities also still work in the hyperbolic world. Hyperbolic cosecant is 1 over hyperbolic sine. Hyperbolic secant is 1 over hyperbolic cosine. And hyperbolic cotangent is cosine, hyperbolic cosine over hyperbolic sine, which is just the reciprocal of hyperbolic tangent. So these are the 6 hyperbolic trig functions that you're going to have to know. Cosine and sine, there are explicit definitions. The other 4, we just use the identities of. There are also some basic identities that we're going to have to look at, and not a lot of them, but there are a couple of things that we'll run into when we're working with hyperbolic functions throughout this semester. So if you remember back when you learned about even and odd functions when it comes to trig, you probably remember at some point that you learned that sine was an odd function and cosine was an even function. Well, actually, it's the exact same in the hyperbolic world. And what that tells us is that if you have a negative value inside of your hyperbolic sine function, you can bring that negative out to the front and just write it as the negative hyperbolic sine of positive x, because that right there is the definition of an odd function. Hyperbolic cosine, just like regular cosine, is an even function. So this is actually best case scenario. You can see that the negative inside of your hyperbolic cosine actually just goes away and there's not a negative at all. This is the definition of an even function, and that is what hyperbolic sine and cosine can be converted into. There are also a couple, if you remember from trig, Pythagorean identities. Now, in regular trig, there were 3 of them. There were sine squared plus cosine squared equals 1, tangent squared plus 1 equals secant squared, and 1 plus cotangent squared is cosecant squared. In the hyperbolic world, there's only 2 that I need you to know, but they don't work the same as it did in regular trig. The first one is that hyperbolic cosine squared minus hyperbolic sine squared is going to equal 1. The big difference here is that it's not addition anymore, it's subtraction, and it must be in this order for it to work. And then also another identity we might see popped up is that 1 minus the hyperbolic tangent squared value is going to equal hyperbolic secant squared. So make sure you know both of those hyperbolic Pythagorean identities along with the idea of even and odd above. So let's do our first example to kind of show you how you can evaluate some of these hyperbolic functions. So I've made up just 3 basic ones. We're going to find the exact and approximate values of hyperbolic sine of 4, hyperbolic cosine of 4, and hyperbolic tangent of 4. Now over here on the right, if you remember from a little bit earlier, we defined hyperbolic sine, oops, sorry, not plus, it's minus, is that it's e to the x minus e to the negative x over 2. So when you're asked to evaluate hyperbolic sine of 4, you just need to replace those x's in this formula with 4's. So that would be e to the 4 minus e to the negative 4, all divided by 2. And that would be the exact value of hyperbolic sine of 4. Now on WebAssign, when you're doing your homework, if they happen to ask you for the approximate value, just type that into a calculator you have and just give it the approximate answer. I did this a few minutes ago, and I found this to be 27.28992. Just round your answer to whatever WebAssign is asking, if that's what it's asking for. All right, hyperbolic cosine of 4. Once again, the definition of hyperbolic cosine is going to be e to the x plus e to the negative x, all divided by 2. So once again, I'm going to plug 4 into this, into my identity, which will be e to the 4 plus e to the negative 4 divided by 2. And your value is not going to be much different. That's the exact value. And then if you just type this in your calculator, make sure you can find your E button, you will find this to be very similar. It is 27.30823. And then once you get those two explicit answers, finding any of the other 4 is just using your basic identities. So as far as hyperbolic tangent goes, all you have to do is do what is the hyperbolic sine of 4 divided by the hyperbolic cosine of 4, because that same quotient identity still happens. So this would be the 27.28992 I found on the first part, divided by the 27.30823 I saw on the second point. And if you type that into your calculator, you're going to get a number very, very close to 1. How about 0.999329? And that's how you will evaluate hyperbolic trig functions. Like I said, so all you got to do is plug the numbers you're evaluating into your hyperbolic formulas and then use identities if you need to. All right. The other good thing about hyperbolic functions, trig functions, is that you can use them to show basic identities. So for example, let's prove that the following is true. This is an identity I did not give you. Let's show that the hyperbolic cosine of x minus the hyperbolic sine of x is going to equal just an exponential function, e to the negative x. So the big challenge with this problem is that all you're looking to do here is to simplify this left-hand side, because you're not going to be able to do anything with this e right here. I want to see, can I turn these two hyperbolic trig functions into e to the negative x? So from the definitions I gave you earlier, we can say that hyperbolic cosine is e to the x plus e to the negative x divided by 2. And I'm going to subtract from that the definition of the hyperbolic sine, which is e to the x minus e to the negative x, all divided by 2. Since these do have common denominators, all I have to do is I can put these together, and I can make this one big fraction being divided by 2. Now do be careful here, because you're going to have e to the x plus e to the negative x, but since you're subtracting this entire second fraction, that negative's got to get applied to both of those two terms in the second numerator, which would make it minus e to the x plus an e to the negative x. And what that allows us to now do is that e to the x minus e to the x cancels, and you're going to end up with 2 e's to the negative x, all divided by 2. And very nicely, the 2's cancel here, and you get a simplified answer of e to the negative x, which is exactly what I wanted to show. So we have just shown another identity that the hyperbolic cosine minus hyperbolic sine, as long as the angles are the same, it will always be e raised to the negative x power. So that leads us into the next thing. This is where your actual calculus comes in. So we kind of got the basics out of the way, and there's a lot of rules here. So like I said, if you need to pause the video and write these down, that's fine, but we got a lot of rules to go over. So first off, what are the 6 derivatives of the hyperbolic trig functions? Some of these are going to look very similar, and some are going to have a little bit unique differences in what you learned back when you did trig derivatives in Cal 1. So let's just start from the far left, and I'll work down the 3 basic ones, and then we'll move over to the right and do the 3 reciprocals. So on the left, the first one is not much different. The derivative of hyperbolic sine is just going to be hyperbolic cosine, similar to how sine became cosine in regular derivatives. But your second rule is the first big difference. Back in Cal 1, you said the derivative of cosine was negative sine. Well, that's not true here. The derivative of hyperbolic cosine is actually positive hyperbolic sine. So essentially, the derivatives of these first two just kind of go back and forth. So your derivatives will be oscillating between hyperbolic sine and hyperbolic cosine. All right, and then the other big one, hyperbolic tangent, is not really any different than Cal 1. The derivative of hyperbolic tangent is going to be hyperbolic secant squared, very similar to how it was in Cal 1. Now you'll notice sine, cosine, and tangent, your 3 main trig functions in the hyperbolic world. When you take the derivative of those, all of them remain positive. The 3 reciprocals that we're about to go over on the right-hand side of your screen, these are all going to be negatives, but similar to the derivatives you did in Cal 1. So for example, the derivative of hyperbolic cosecant is going to be negative hyperbolic cosecant times hyperbolic cotangent. The derivative of hyperbolic secant is the negative, this one's different, it's negative hyperbolic secant times hyperbolic tangent. And then the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. It's a mouthful sometimes. So essentially, the main core of the derivative rules is the same. The difference is going to be is knowing which ones are negative and which ones are positive. The only 2 that are different are actually reciprocals of each other. Hyperbolic cosine is not negative when you do the derivative, but hyperbolic secant is going to be negative. So make sure these 2 in the middle, just be careful when you're learning those 6 derivative rules of the hyperbolic functions. And then the other thing you covered in Calculus 1 was how to take derivatives of inverse trig functions. Well, hyperbolic also exists in the inverse trig world, so you will need to know these 6 rules as well. So let's kind of run through these because they don't match up really very well with the normal inverse trig that you learned in Cal 1. So once again, we'll do the 3 on the left first. The derivative of hyperbolic inverse sine, it's a mouthful, is going to end up being 1 over the square root of 1 plus x squared. The derivative of the inverse hyperbolic cosine function is going to be 1 over the square root of x squared minus 1. And the derivative of the inverse hyperbolic tangent function is going to be 1 over 1 minus x squared. None of those really look very similar to what you learned when you did regular inverse trig. So they are all different. So once again, it's going to take a little bit of memorization and learning between now and your first test. So start learning these new derivative rules as we go along. All right, on the right-hand side, you have the 3 reciprocals. We won't see these as much, but let's make sure we note them down in our notebook. So for the first one, the derivative of inverse hyperbolic cosecant is going to be a negative 1 over the absolute value of x times the square root of x squared plus 1. The derivative of inverse hyperbolic secant is going to be negative 1 over positive x times the square root of 1 minus x squared. And then here is one of the cool things, and this is the only one that really helps here. The derivative of inverse hyperbolic cotangent is the exact same thing as the derivative of inverse hyperbolic tangent in this case. All right, so those 2 match up exactly. Once again, that's the only one that's really nice about it. The rest of them are a little bit unique, so make sure you start learning this. So for the rest of this video, what I want to do now is I want to run through, and we're going to do just taking derivatives of hyperbolic trig functions and inverse hyperbolic trig functions. And then we're also going to mix in some other rules that you should have learned from the Cal 1 course. So for example, what is the derivative of the hyperbolic sine of x squared? So first off, you have to remember that this is actually going to be a chain rule just like it was in Calculus 1. So you have a trig function, even though it's hyperbolic, of something on the inside. So when you take the derivative of this, the chain rule says you start with the outside function. The derivative of hyperbolic sine is going to be hyperbolic cosine. You leave the inside of your hyperbolic function alone, which is x squared, and you multiply by the derivative of the inside, which would be 2x. I would probably clean this up a little bit just to make it look prettier, and I would move the 2x to the front, and this would be 2x times the hyperbolic cosine of x squared. So just because we are moving into the hyperbolic trig world in this section doesn't mean you can't forget your core rules from the early on in Cal 1. You still have to apply the chain rule in this scenario. So very good. Some other rules, even though hyperbolics have e's involved as well, you have to also remember a couple other rules. So for example, number 4, what is the derivative of f of x equals e to the x times the hyperbolic cosine of x? Well, in this case, there's 2 rules you have to remember, even though one's a lot easier. The big rule here is to notice that these are 2 separate functions being multiplied together. So overall, you're going to have to do the product rule. You're also going to have to remember your derivatives of how to do e's, and then also your new rules, the derivatives of hyperbolic trig functions. So when I go to write out the product rule here, I would say that f prime of x is going to equal your first term, which is e to the x, multiplied by the derivative of the second. The derivative of hyperbolic cosine is hyperbolic sine, then plus your second function, which is the hyperbolic cosine, multiplied by the derivative of the first. The derivative of e to the x is just e to the x. Now, normally in product rule, it wouldn't be a lot of work here, but this actually simplifies a little bit further. So what I notice here is that both of these functions share an e to the x in common. So if I factor an e to the x out of both terms, I am left with the hyperbolic sine of x plus the hyperbolic cosine of x left over inside the parentheses. We know what both of those are equal to. We have to go back to our definitions of hyperbolic trig functions and plug those in. So I would say that this is e to the x times hyperbolic sine is e to the x minus e to the negative x divided by 2 plus hyperbolic cosine is e to the x plus e to the negative x divided by 2. Since they have common denominators, we can put those together so that e to the x out front stays there. And when I add these fractions together with a common denominator of 2, you should get e to the x minus e to the negative x plus e to the x plus e to the negative x. Similar to earlier, just a different term this time, your e to the negative x terms are actually opposite, so they do end up canceling. And this gives you e to the x times 2e to the x's, all divided by 2. And once again, from earlier, we saw this. Your 2 divided by 2 cancels, but the difference now is you have to multiply this e to the x by that e to the x that we factored out a little bit earlier, and you should get a final derivative of e raised to the 2x, which is kind of neat to see. That an exponential function times a hyperbolic trig function, the derivative of that just comes out to be an exponential function in the end. So very good. You just got to remember your rules. And there's an extra step of also knowing the definitions of hyperbolic sine and cosine. All right, so that one had product rule. We've done chain rule. You're probably guessing what's coming up next. And if you guessed quotient rule, you are 100% correct. We have to make sure we also remember our quotient rule from Cal 1. So we want to take the derivative of 1 plus hyperbolic sine over 1 minus hyperbolic sine. All right, so what I'm going to do is we're going to do the quotient rule because you've got a function of x on top and a function of x on the bottom. So let's kind of say the quotient rule out loud here. This would be your bottom which is 1 minus the hyperbolic sine of x, multiplied by the derivative of the top. 1 goes away, and the derivative of hyperbolic sine is hyperbolic cosine. All right, so minus the top, which is 1 plus hyperbolic sine, times the derivative of the bottom, which would be negative hyperbolic cosine, because the negative kind of comes along for the ride. All of this is divided by the bottom squared. So 1 minus hyperbolic sine of x all squared. And if you recall back to Cal 1, what you'll have to do now is simplify the numerator all the way out, and let's see if anything simplifies. So I'm going to distribute hyperbolic cosine to both of these terms. So that would be hyperbolic cosine of x minus sine, or hyperbolic sine, times hyperbolic cosine. All right. What I'm going to do here is that I notice that this negative and this negative right here are going to end up being multiplied. So that really just becomes addition here. And I'm going to distribute this hyperbolic cosine to these two terms, but everything's going to stay positive. So it'll be plus hyperbolic cosine of x plus hyperbolic sine of x, and squeeze this in here, times hyperbolic cosine. All of this over 1 minus the hyperbolic sine of x all squared. And while this one doesn't have a fancy identity or anything, what does happen is this second term and this fourth term are actually opposites of each other that cause them to cancel. And what that allows you to do is put these two hyperbolic cosines together, because there's two of them, and you'll have 2 times the hyperbolic cosine of x divided by 1 minus the hyperbolic sine of x all squared. And that's as far as you're going to be able to simplify that one. Expanding the denominator is not going to be very helpful, but very good. All right. And then to wrap this section up, I want to do a couple of the derivatives of hyperbolic inverse trig functions, just to show you how those work. I'm primarily going to focus on the ones we're going to see the most going forward, even though all 6 are important to learn on. So in this case, we've got the inverse hyperbolic sine of x. So what I have to remember from that chart I gave you a little bit earlier is that the derivative of the hyperbolic inverse sine of x, remember, hopefully you wrote it down, is going to end up being 1 over the square root of 1 plus x squared. So in this example, this is a basic hyperbolic sine. I need to turn this x into whatever my input value of the inverse hyperbolic sine function is. So Rx is actually going to turn into a negative 2x when I take the derivative. So down here on the left, I can say that f prime of x is going to end up equaling 1 divided by the square root of 1 plus, replace the x in your formula with the input, which is negative 2x, and don't forget to square it. And then once again, the chain rule pops up, so you must now take the derivative of the inside, which the derivative of negative 2x is negative 2. The good thing about inverse hyperbolics and even inverse regular trig is there's not much to simplify here. Negative 2 times 1 puts a negative 2 on top. And then on the bottom, if you were to square out your term, this would be 1 plus 4x squared. And that's really the best you're going to get. But the important thing to note here is, unlike regular hyperbolic sine and cosine, where you're going to have more hyperbolic trig functions, when you do the derivative of inverse hyperbolic trig, it all comes out to be rational functions. Just make sure you shouldn't have many hyperbolic stuff floating around. Well, very good. All right, and then to wrap up this first video and this first section of material, let's do one with hyperbolic tangent, because that's probably the other popular one you're going to see a lot of. So just to kind of end on a high note, we're going to have to do a little bit of simplifying here. All right, so before I even start this problem, I'm actually going to rewrite this square root function because that's going to be a little bit difficult to do as it sits. So I would actually write this as x times the inverse hyperbolic tangent of x plus the natural log, and I'm going to rewrite this square root as 1 minus x squared to the 1/2 power. Because you're going to have to do some form of chain rule here in just a few minutes. All right, so now as far as the derivative goes, starting with the first two terms, x times the inverse hyperbolic tangent. That is going to be a product rule that you have to do again. So f prime of x is going to equal, so do your product rule. This would be your first, and from that chart I gave you, the derivative of inverse hyperbolic tangent is 1 over 1 minus x squared. All right, then plus the second, which is the inverse hyperbolic tangent of x, times the derivative of the first, which is just 1. The second part is actually something you learned in Cal 1 of how to take the derivative of a natural log function. So recall, when you take the derivative of a natural log, whatever is inside of the square, whatever is inside the natural log, that goes on the bottom, which would be 1 minus x squared raised to the 1/2. And then on the top, you take the derivative of that and put it in the numerator. So that would be chain rule. So you would bring a 1/2 to the front, leave the inside alone, drop the power down by 1 to the negative 1/2, and then multiply by the derivative of the inside, which is negative 2x. And the challenge here is this is a lot of reducing, because it's going to come out to be actually a very nice answer if we do this correctly. So what I notice here is that if I multiply these first two terms together, that would be x over 1 minus x squared. Multiplying by 1 doesn't do anything, so this is just going to remain the inverse hyperbolic of tangent. And here's where all the simplifying happens. So this is going to end up being this 1/2 times this negative 2x is going to let me write this as a plus negative x times 1 minus x squared to the negative 1/2 over 1 minus x squared to the positive 1/2. Now, really, I'm just focused on this second piece. So let's just focus on this part. All right. This negative 1/2 power on top, I can bring that to the bottom to make this a negative x over, and you're actually going to end up with the same term twice. You're going to have two separate 1 minus x squareds to the 1/2. Because once again, all I did is I took this term right here and I brought it to the bottom. Since they are the same base, you can add the exponents together, and this should give you a negative x over 1 minus x squared, and then 1/2 plus 1/2 just makes this the first power. So putting this all back together in my answer, your derivative should say x over 1 minus x squared plus the inverse hyperbolic tangent of x, and then minus x over 1 minus x squared. And best case scenario here, two of your three terms cancel each other. The first and the third cancel, and you are left with the inverse hyperbolic tangent of x. That is the derivative of the original problem. And that's probably the most in detail you would have to get on this other problem. So that ends the video for section 3.11. So this was a section that y'all skipped over in Cal 1 that I needed to go over with y'all. In the next video, we will move into chapter 4, and start the big part of Calculus 2.